And thank you, Arijit, for calling. So, as Professor Rahul discussed, that set of physicists looking at computational biology. So I'm not a biologist, or I have not been trained as a computational biologist. I am control theorist. And some point of time, I converted to biologist thanks to my students, and particularly to computation. So the most of the work I'm going to talk about is from some of my students who's got me nice problems, and I looked at that as a control problems along with them and solved it. So biology mostly come from them, and I'm the one who is trying to see how we can actually analyze the data and models. So I'll start with the motivations and approaches. What is my motivation? Why we want to do it? And I'll talk about 3 stories which last 5 years we have been working on. First one is about 2 biological networks and how they interact with each other, and how we can use that information and create what I call it minimal models. Second story is about integration of reactive species with the metabolic network. And this is story with one of my colleagues, Professor G.K. Suresh. And the last one, which started as a small discussion project over tea, and now it become a nice project on understanding one of the syndromes, which we model as a multi-tissue models, how we can actually combine information from different tissues and try to understand the systems. And I'll just conclude my talk with what we are looking at in the future. So, need not to say that biological systems are very complex systems. So you guys know better than I do. So when I look at it from the control point of view, we look at the inputs which are affecting the system, and there's output which actually appears to as a effect of the system, which we call phenotype. The input can be innate factors, some genotypes, or maybe the external factors, which typically like a gut microbe, nutrients, pollution, etc. You can keep adding on that. And last many decades, people have collected a lot of data, and our objective is to see how we can actually use this data to understand biological systems. Sometimes try to see if there's a possibility of diagnosis. Some students are interested in using this data and these biological systems to understand how we can actually look at the therapy or drugs, etc. So today's talk is mainly about how we can use this data to understand biological system and model those systems. So as a control theorist, we like a feedback a lot. And some of the interesting question when I looked at this thing, I can ask is how to get better understanding of biological networks, basically how these inputs are actually transferred to the outputs, which is the phenotypes. Particularly in the disease conditions, because in a case of disease, the biological systems actually cannot get perturbed from the output, but cannot give different kind of output. And it does not happen in a what I call it simple manner, because typically biological systems are considered to be robust systems. So how it happens, we wanted to understand. And for that, first we have to see, can I build the models for different systems and then do some comparative analysis. If I understand this first, then what I can do is I can manipulate these systems to get a desired output, which we typically call it going from disease condition to possibly to the normal condition, or get a disease-free. Both of these things we do in a control theory quite a lot. We build a model using input and output, and we manipulate the systems to actually get a desired output. It is very easy to do it in industrial processes, although not that easy, but still I can say easy. But when it comes to biology, it is quite difficult. And that makes the problem beautiful and interesting. So what we did is, our philosophy is, can we exploit the different data available to us and build reconstruct network models. We also try to see if we can do automatically extension of the models. This is what I talked about last time, using some of the natural language processing models. And also we try to see how this some of the inputs of interest to our collaborators interact with this biological entity to produce certain phenotypes. And if we can understand those phenotypes, one of the interests which we have is take this model and try to see if I can come up with some optimal therapeutic intervention for the diseases over a time and try to manipulate some of this input to get a disease free. So I'll start with a first story where I will discuss how we try to integrate two models. One is metabolic and signaling networks. Although the philosophy is only for metabolic and signaling networks, it can be worked for the metabolic and signaling regulatory networks or any kind of networks we want to actually combine which in the bioprocesses. So the idea here is typically people look at signaling network alone, look at the using some of the ordinary differential equation and try to understand how the fractional activation changes with the time. Similarly, there is a huge community which looks at metabolic networks, which is typically at steady state, and there are flux balance analysis based approaches which put some constraint and objective function in a particular scenario and try to understand how the metabolic pathways are actually getting lightened up or using biological systems is using those pathways to perform certain tasks. And the question we have asked that can we actually combine this kind of two different kind of approaches. One is based on the optimization and another based on the ODE differential equation based. Why we are interested in that? Because often we can see that biological systems have a lot of feedback, correct? They actually, it's not like the metabolic pathways work by themselves or signaling pathways work by themselves or regulatory pathways work by themselves. They actually interact with each other and do a lot of processes. So what we started with, we looked at the metabolic network analysis and saw that there's a standard way of solving this problem called flux variability analysis or flux balance analysis. And we say that, okay, we'll start with the flux variability analysis and get what is the mean flux and maximum flux which can go through different reactions in these particular metabolic processes under metabolic conditions. If you have that idea, can we actually exploit it in this particular networking? So typically in the signaling networking, when we solve it, we actually set up a set of ODEs and try to see what is the fractional activation of the particular signal, which is indeed going to affect some metabolic processes. So what we have to do is somehow we have to actually connect this output with this constraint and objective function, and this output with somehow the initial conditions or the update the initial condition of the systems. So what we try to do is we try to actually come up with the approach which allows us to actually go from the signaling activation, fractional activation to metabolic networks changes. So what we have to change, we have to change the bounds and provide the feedback from the signaling networks which actually either increases bound, or lower bound, or upper bound. So in that, by using the activation of the molecules, we actually can change the bounds. And again, once we change the bound under that new bound condition, we can actually simulate the system for some time delta t. And then again, we have a new steady state distribution. We get this steady state distribution and try to connect metabolic network pathways with signaling pathways. So now we have to give a feedback from metabolic to signaling, and we actually can do this two manners. One is if there is a directly flux is affecting the fractional activation, we can actually update that one. Another one which is more interesting because often the metabolite concentration itself actually affect the signaling pathways. So in that case, we can actually use that particular concentration itself to actually give a feedback to the signaling networks. So we did again that way. We actually used steady state distribution and actually computed some new updated initial condition and then simulated our signaling pathways. And this, we keep doing it until we achieve the steady states. Okay? It means that there is, after certain time, there will be no changes in the signaling fractional activation or change in metabolic flux distributions. So this is a philosophy we started with, and we actually look at first simple model, hepatocyte. We started with some more complex model, but I didn't like it, so we say, okay, we'll take a simple models available in the literature, where we model insulin glucagon signaling in a hepatocyte metabolic networks, where we took simple 62 reactions where glucose consumption pathways and glucose production pathways are there, which tells a glycolysis, glycogenesis, or glyconeogenesis, etc. And once we have this, what we did is we actually want to actually have a signaling network pathways. So we got nice pathway from one of the group in IIT Bombay, which has around 31 molecules, where the input is glucose concentration, concentration of amino acid, and concentration of fatty acid. And we say, okay, we'll study how the glucose concentration affects or can be changed by integration. So one of the pieces which we have to actually figure it out is what should be the objective function for these pathways, because this is a small pathway, what we can do with it. And we decided that we can actually take this objective function which maximize the flux through these two reactions. And these two reactions, one reaction support the glucose consumption, another supports the glucose production. So there is a balance between both of them in a different situation. Now, in this particular example, the glucose concentration is the one which gives the feedback to the signaling molecules. So we have to actually come up with some kind of model which allows us to take our concentration at t-1 and produce concentration at t. So we got some data in the literature, and we actually found out this tuning parameter which reflects the actual flux analysis. And we obtained this parameter using some of the fasting concentration of glucose data, and then we integrated the model. And then we simulate the model for low glucose concentration and the high glucose concentration situations. So idea here is to understand whether if system is behaving in a normal system is behaving in a normal manner or not. So this is a normal model. So we actually started with the very lowest glucose concentration and try to see whether by simulating can we actually reach to the normal range of the glucose. And indeed, as we simulated the integrated models, there is a feedback from the system and which start producing glucose and try to bring the glucose concentration to the normal range. And these are some of the important glucose fluxes over a time for different reactions. Similarly, we look at the high concentrations. If I have a high concentration, start with the 180 here, we started with it, and we see that again, slowly it decreases and getting a concentration in a range which is acceptable clinically. Again, we looked at the concentration, which reactions are getting affected, and you can see some of the important reactions are actually getting affected, and some of the time they actually consume the glucose because it's a high glucose concentrations. And that is one of the interesting part. We saw that when we integrate two models, we actually, with a very minimal model, we can actually replicate some of the physiological conditions. And this tells us the feedback of the importance of the feedback. Rather than studying two models separately, why can't we actually bring them together? And giving a feedback is always good. It provides us far better realistic model with a simpler version than the complex models which will be difficult to sometimes analyze. However, the reviewers don't like that. So now students are looking at larger models, which is really physiological models, type 2 diabetes, and the non-alcoholic fatty liver diseases, and try to see can we actually show it at a larger scale. As a theorist, we are also looking at, there is certain interesting aspect. You can see that is some robustness is there, correct? Because in the model, because if I start with glucose concentration which is less, it produces exactly new steady state, the same kind of steady state. Here also, if I start with part of the system, it produces the same kind of steady states. And that is one of the interesting aspects of the biological system. There's a robustness. So how can we actually understand the robustness in the system? Also, we are also looking at the fragility of the biological systems, because often what happens is some small manipulation happens and the systems actually collapse like a house of cards, and we don't know why. So we are looking at those two aspects, theoretically try to understand why this particular model robustness, as well as we want to actually break the model and see where it will break and why it's breaking, the fragility. The next story I would like to talk about is reaction species. This is work we done with the Professor GK group, who are actually working on reactive species for many years and try to understand the role of reactive species in a different biological systems. And we started to work with him and try to see, can we actually create a comprehensive reactive species module, which through data curation, and integrate with the genome scale metabolic models. And in this case, we were interested in looking at cancer metabolism. One of the reasons why we are interested in cancer metabolism, because reactive species has an important role to play. There is a lot of talk about redox homeostasis and metabolic reprogramming happening because of reactive species. And RS, antioxidant, and redox homeostasis are some of the hallmark of the cancers. So what we thought that if we bring the reactive species to the module, to the system, can we actually learn more about cancer cell or in general cancer metabolism? One of the challenges we had is because we want to do it, we went to the standard genome scale model, which is for the human reconstructions are available, and many of them do not have that much comprehensive reactive species reactions. They have some reactions like 30, 40, but there is no detailed information about this many biochemical reactions involving the reactive species. So we started to curate reactive species, and we started curating it manually with the help of some students, by scraping some of the databases, looking at incomplete reaction, verifying the mass and charge balances, and we finally have this reaction species module where we added around, we have around 240 reactions and 176 metabolites. This is the addition to what is available in the Recon 3D or Harvey-Harveta or human GEM model. Once we have that, what we want to do is we want to integrate this module with standard genome scale models and try to understand how we can actually, is there any difference in understanding the cancer metabolisms at all. But what we did is we typically build a context-specific model, means for particular context. In this case, we chose CRC colon cancer. One of the reasons choosing for colon cancer because I think GK was working already with the cancer, and they have some experimental data as well as some more experience with working with the cancer. And what we did is we took a colon as well as CRC cell line cancer transcriptomics data and build a model which is without any RS module, which is a context-specific model for both conditions. And then we integrated this module with the RS, this particular model with the RS module, and try to see whether we can actually get a better insight into the RS module with this context-specific module or without RS module. And when we did that, when we actually incorporated RS module, then we got many pathways, which is here I talk about average flux span ratio values, which is average in the sense of all the reactions which are dysregulated, and we compute it. And we saw that these are the pathways are also available in the literature, which are typically dysregulated in a CRC RS module, while in the CRC module it does not show that significant changes. So it shows that by just adding 240 more reactions, we can actually get far better insight into the cancer metabolism. Particularly, students found a very interesting fact that because ferroptosis, which is one of the cell death related to an intracellular iron-dependent form, which is quite predominant in our model. Means we can found that ferroptosis as one of the metabolic vulnerability in the CRC cancer, and there are certain dysregulation. You can see this. This is the very comprehensive study which shows that how the fluxes on an average is different in a simple colon model and the colon model with the RS module. Similarly, and both sides upregulated, downregulated, both are have been shown, and we are now actually looking at how actually it indeed help us in understanding ferroptosis better. So some of the conclusion here we can say that is we have developed RS module. This module is available. If you want to use it, it's publicly available. We have make it available, you can use it and understand for your diseases what is RS or reactive species plays a role in. It helps us actually to understand some of the metabolic pathways in a cancer. We actually use this also for the breast cancer as well as the ovarian cancer. Also in future, we are trying to see some analysis to discover therapeutics and biomarkers using some gene literature analysis. Okay, yeah, I have 5 minutes. So I'll quickly discuss the next story, which is metabolic modeling using multi-tissue, for the multi-tissues, where it's about PCOS, which is polycystic ovarian syndrome, and it is highly, one of the, in a modern time, it is quite prevalent in many women across the world, and in particular in India. And once we were discussing over a coffee about that, and we thought, okay, let's see, it is very interesting because the syndrome rather than disease, so you have to involve multiple tissues. So typically there are a lot of metabolic syndromes are involved in polycystic ovarian syndrome, which hyperandrogenism, dyslipidemia, insulin resistance, which is one of the more challenges. And what we try to see that can we actually take this and convert into metabolic pathway analysis kind of models, which we know. The only challenge is that when we try to do literature survey, we realize it is more complex than, I don't think so, it is working. More complex than we thought. So finally we decided, let's look at all the tissues model and see how we can integrate these tissues together using some certain conditions. So our objective was the construction of multi-tissue models for the PCOS and the healthy conditions. So we went to the literature, found some data sets which are actually age and BMI matched for the women, and we found the healthy and women and the PCOS women together. And we got some transcriptomics data. One of the challenge here was the data coming from the different sources. So we have to normalize somehow. So we try to come up with something which help us to normalize in a logical manner. And we combine this with our human genome metabolic network and use some other evidence to actually get model for 4 tissue types: adipocyte, skeleton myocyte, granulosa cell, and the oocyte. Granulosa cell and oocytes are near the ovary, while the adipocyte and the myocytes are different tissues. And what we did is, typically, we went to the literature and tried to see how the metabolites are transforming. So in case of oocyte and the granulosa cell, it is typically transformed through the extracellular media, which is basically because of the proximity in the ovary. While the adipocyte and the mesocyte, they have to actually involve the blood compartment, and we went back to the some kind of metabolomics to see what are the metabolites which are there in the blood and what are the transforming, and based on that we created the connections. And so when we created a connection, we actually run the simulations using the flux balance analysis, using the simple objective of maintenance, and try to see whether the flux values are different and what are the dysregulated pathways in general in these systems by doing comparative analysis between PCOS and the non-PCOS women. Okay, this is just an overview of how we actually integrated it. In the interest of time, I will leave it for a while. But what I wanted to tell you that when we actually integrated this model and tried to understand the pathways in a different compartment, there are some key metabolic indicators for the PCOS has been actually shown that one of them is the transportation of amino acid between different tissues increase the transport of bile acid salts from the blood, which is known to be conjugate to the androgens. So these are some of the metabolic dysregulation which are there in a PCOS in the literature we found using our model. And now we are trying to look at more and more in detail are there as possibility with some of the biologists in the department. So as I told you that our main goal is to actually understand biological processes using different kind of data. But we want to use control and learning theory to do that. And we do not want to leave the first principles at all, because I think that in the world of crazy data-driven or black box approaches, the first principles keeps us grounded, because this provides a lot of insight which is difficult to get using some of the data-driven models. And in future, we want to continue with that and try to see that we can actually create a cell-based model by integrating different like regulatory networks and the signaling networks together and create for the disease normal case cell a model, in silico model, which we can actually simulate whenever we want, and possible in the future, if we have a patient-specific data, we can do for the patient-specific simulations and hopefully get a personalized medicine one day. Yeah. So I would like to acknowledge some of the students who have worked on a different path, particularly the Pawan, Subhashri, and Prashant. And Dinit has worked on most of the simulation. And right now, Trilochana is working along with Pawan for some of the problems. And the GK and Raghu are the main collaborator. In addition, time to time, other people gives some kind of inputs. And thank you for time. And we have a wonderful campus.
So it's very complicated to actually measure uptake and secretion rates so that you make them as inputs for the multi-tissue model.
Yeah.
Can you explain, if it's possible, can you explain how did you estimate those rates from the
No, we have not estimated those rates. We only looked at what are the metabolites which are actually exchanging. Okay, and then we are simulating the model.
Achha, so the assumption is that it's abundant.
Yeah, its assumption is it's available for the exchange. Yeah. So we are not actually estimating in anything. There's no experiments here involved. We are just simulating and finding out what's happening under certain conditions.
Okay. Thank you.
Hi, Nirav. That was a great talk. I have one question in each of your stories. Yeah. I'll try to keep it as short as possible. The second one is the shortest question. I needed a clarification. You had these reaction fluxes versus counts.
Yes.
So what are those counts you're talking about?
Which, this one here?
No, the second one, yeah. This one. The next slide, please.
Next slide here.
Yeah, here you have.
This is the distribution of the fluxes.
So this is based on flux sampling.
Sampling, yes, exactly.
All right.
Yeah. This is sampled for each solution. Yeah.
Okay. So now that you're here, can we go to the third problem again? Your picture that you were just showing. Yeah, the one before that.
Okay.
The methodology. One before that. Yeah, so here when you use your RNA-seq data and normalize it, right? So what kind of thresholding algorithm do you use to finally create your metabolic model?
So
and in addition to that, once you apply the init algorithm, how large are these models? How many reactions do you have?
Okay. So the first question is thresholding algorithm. So I think in this one we used our own thresholding algorithm, which is still a bioecho paper is there, which is we use something local Guinea-based coefficient algorithm to do the thresholding, which allows us to get the co-reactions. And our comparative analysis with the local T2 and on stand-up, which is new one, shows that we are doing better than that. So that is one we use. I think we have used it here. Apart from that, I think students have used also local T2 to just check to do that, to see whether we are getting some new co-reactions or not. Regarding the number, I don't have an exact number, but most of them I have around 7,000 reactions, 7,000 to 10,000 range.
And do you remove the blocked reactions here when you have your final model, when you have the multi-tissue model?
So I think there are very few block reactions are there, but I can check and find it out later.
All right. And then coming back to your first story, where you were integrating the metabolic model with the signaling model, right? So if you go back to your signaling network, so I was just curious because I didn't see any ATP over there, right? So because your reactions have, I think some of the flux reactions that you show have phosphorylation and kinase and all of that.
Yeah.
And ATP is one of the key molecules that connects metabolism to signaling.
Yeah.
So I was just wondering, how do you actually account for, ATP
Okay.
and the connections between the two networks?
See, this network we have taken from the literature. So we only look at the one connection, which is the concentration of glucose right now. So I have to see if we can actually look at the ATP also. So I don't think so we have looked at the ATP. And I have to check detail of the model. But in this particular case, both models are available in the literature. So we have not built any model. Only thing we did is to look at one input, which is to the signaling one, which is the glucose, and what is its role in general.
So then maybe I misunderstood. Do you integrate these two models, the metabolic model? So what are your connecting molecules between these two networks?
So currently in this model is only glucose.
It's only glucose.
Yes, that's what I told you. The glucose is the only molecules which we have looked at it, because one of the reasons is that data was available, and it helps us to understand with one molecule itself some mechanisms. But yeah, it's a good question that we can look at the ATP also.
Nice talk. I just have one question. So for the context-specific model, have you used bulk RNA-seq data or a single RNA-seq?
This is a bulk RNA-seq, all of them. I don't think so. It's any of it is not single cell RNA-seq. Yeah.
So if you can you use single RNA-seq data as well?
Yeah, this is the common question. We can use it. The method has nothing to do with you give us. We want to use it actually.
Oh.
Yeah.
Okay, thank you.
Yeah, thanks. Because most of these are published data available, and so there are not much sequential data, single cell data are available yet in public. So,
Thank you.
yeah, thanks.